This is what in machine learning you would call a neuron. It has one input and one output, and inside it has two parameters, w and b, which are arranged in a linear equation wx plus b, where x is the input and w and b are tunable parameters. The goal in this video will be to tune them best to fit some given data. So now, if we move over to Desmus, we can see how the model looks like. We can tune W and B, the parameters, and they change the tilt, which is the slope of the line, and the intercept of the line, respectively. Using just these two parameters, we can in principle model every linear equation that can be formed, and hence every possible line in this plane. So here's a classic starter example, house prices and their areas. If we train a linear regression model to predict house areas based on their prices, which is the given data, then we see that the line, which is the model, maps the points, each of which is a data point, more accurately than before. But to make the model better, we first need to know how wrong is it. To do this, we use the cost function. It might seem scary, but it has one purpose. It tells us how far off the model's prediction is from the actual answer. So let's move on to the whiteboard, and here we have got the cost function written down, and in the cost function this term right here, y hat I, stands for the model's prediction for the input x to the I. So let's clear some notation first. What does this even mean, right? So this basically means if we have some data, for example this data right here, area and price, if we give the model the area as input and the model outputs the price, then the input will be called x while the output will be called y. So this right here is y1 and this is x1. This is x2, y2, x3, y3 and x4, y4. So if we have an ith example, ith data point, ith training example, it can be written down as xi, yi. So this, for example, is xi, yi, xi, yi. So let's see how this works. For example, if x1, the first input is 23 and the weight is 1 and the bias is 2, then the model will predict 25, so that will be y hat 1, and y1 will be 19. So x1 is 23, y1 is 19 and y hat 1 is 25. So what is the difference between y hat 1 and y1? It's 6. So 6 is how far off the model's prediction is. But the problem with that is, in the cost function we want to minimize that error, how far off the model's prediction is. But if we get a negative value that is farther than, for example, a value of 0, but still the model will think that -2 is better than 0. So we square the value so that the error always stays positive and negative values are not an option. Here you might think that why don't we use an absolute value? We could use an absolute value of this error. This right here is called the error. Y hat I minus yi is the error for the ith training example. So we could use the absolute value of the error, but another benefit of using the square of the error is that it penalizes the larger mistakes more. So when we square the error, if the error was 5, then it would become 25, and it was 2, then it would become 4. So we can see that it penalizes larger errors more, which is what we want. If the model makes a bigger mistake, then we want it to focus on that instead of trying to fix smaller mistakes. So what does M stand for here? M stands for the number of training examples, the number of pairs of x and y that we've got. So for example, in this table, m will be 4 because we've got 4 pairs. 1, 2, 3 and 4, right? So we got 4 training examples. M will be 4 here. So let's uh, try a concrete example to see how the cost function works. M is 4, x1 is 1, y1 is 2 and y hat 1 is 3. So the input is 1, the actual value, the output should be 2, but the model's prediction is 3. Similarly, x2 is 2, y2 is 4 and y hat 2 is 5. x3 is 3, y3 is 6, y hat 3 is 7, x4 is 4, y4 is 8 and y hat 4 is 9. So what will be the total sum of all the errors? It would be 3 minus 2, right? We subtract y hat 1, we find the difference between y hat 1 and y1. That would be 3 minus 2. We square it, then we do it for each term. So the difference is 1 each time, the square is 1. So the total errors all added together are 4. You might be thinking, why do we divide this value by 2m? That's because if we don't divide it by 2m, the more data we have, the larger the error would be, even if the model is not making that big of a mistake. So we divide it by 2m to generalize it to the data and find the average error. So right here we got 1 over 8, 1 over 2m is 1 over 8, and the cost will be 4 times 1 over 8, which will be 1 over 2. Of course, this was a very simple example. When we actually do linear regression, we have hundreds of training examples, data points, and we find the cost over all those data points. You might be thinking, why do we divide it by 2m instead of just m? We do that because we need to find the derivative of the cost function to do gradient descent, which I will talk about later. And for that, if we have 2m, the calculations are neater. That's why machine learning folk like to write it as 2m instead of just m. So let's come back to Desmus because I wanted to show you all this. This is the graph of the cost function. The z-axis is the cost itself, while the x-axis and y-axis are the parameters w and b respectively. So here we can see that the shape looks sort of like a bowl or a cup. And for example, if we start at a random point on this cup, if we take a random value of w and b and we start, for example, right here, it is hard to know what exact values do we need of w and b to reach the very bottom of this chart and to get the lowest cost and hence make the best model. But it is much easier to know in which direction we need to go to get a lower cost. For example, if I am standing right here, then I know that going south will give me a better cost than going north. But it is hard for me to find the exact position, the exact coordinates where the value of the cost will be the lowest. So now we'll cover gradient descent, the algorithm by which the model learns. For this, I want you to imagine yourself walking down a hill. It's hard for you to know the exact coordinates where the bottom of the hill is, but you can easily deduce in which direction you need to go to reach the bottom. That is the essence of gradient descent. So now let's move on back to the whiteboard and start with gradient descent. In gradient descent, first, let us start off with just one parameter w, which is the weight, for simplicity. J of w denotes the cost and w is the weight. So when we plot the cost with respect to the weight, we get this plot, this chart. For example, if we start off at a random point h and the value of the weight at h is 7, how do we do gradient descent to find which direction we need to go in to improve the model and reduce the cost. Well, we need to reach this point as it has the lowest cost. We need to reach this point, right? So first, we find the derivative at that point. You might be asking, what is the derivative? So here, for example, if we have a line and we want to find its slope, what is the slope? It is the rise over run. It is how much the y-axis increases per increase in x-axis. So that would be 2 over 3, right? The derivative is simply when the run, which here the run is 3. When we take the run to be a very, very small number, but not 0. It approaches 0, but it is not equal to 0, if that makes sense. For example, we can take the run to be 0.00001. That would be the derivative. So, you might be saying that this line, it isn't a straight line, it's a curve. How do we find the slope of a curve? Well, we zoom in into the curve, and when we zoom in far enough, we can see that a slope forms. That slope is the derivative. So, for example, the derivative right here at the point h is 3. Then, what we do in gradient descent is this equation right here. W is equals to W minus alpha, which is a small number. It's a constant which we fix, a parameter, times the derivative of the cost function at that point, W. So, if we try a concrete example, the derivative is 3. So, W will be equal to W minus 0.01, which we take to be alpha, times 3. So, W is equals to W minus 0.03. Note that this isn't equality. We aren't saying that these two values are equal. We are saying that the new value of W will be equal to this, the old value of W minus 0.03. We update the value of W each iteration, and we keep doing this until we converge at a point where the cost is at a minimum. For example, after this step we reach J, then we might reach this point, then this point, and slowly we reach this point where the cost with gradient descent converges and the training is finished. That is why I was saying that we divided by 2m. Since we have to find the derivative of the cost function, we divided by 2m, since that makes the calculations neater. Now we will derive the cost function with respect to W and then with respect to B to perform gradient descent. So here in gradient descent, we have seen the example where we only take W as the parameter. When we have both W and B as the parameters, then the update simply becomes W is equals to W minus alpha times the derivative with respect to W of the cost function J of WB. And for B, it becomes B is equals to B minus alpha times the derivative of the cost function with respect to B. So now that we've seen gradient descent, we need to calculate the derivative of the cost function with both respect to B and W so that we can perform gradient descent. So here I've written down the cost function again, and from calculus we know the three rules: the sum rule, the product rule, and the chain rule. Using these three, we can step by step calculate the derivative of the cost function with respect to w and b. So first, let's define f of wb is equals to wxi plus b minus yi. So this term right here is y hat I. So it becomes y hat I minus yi. And g of x can be defined as x squared. So we need to find the derivative of g of f of wb, right? We need to find the derivative of this chained function right there, here. It's a function inside a function. So how do we do that? First, let's find the derivative of f of wb with respect to w. B is a constant and yi is also a constant, so we will not count both of those in the derivative, and xi will define the slope of the line, so xi will be the derivative. And when we find the derivative with respect to b here, then w is a constant and x is a constant, so this whole term becomes a constant and yi is again a constant. So we just have b and it isn't multiplied with anything, so the derivative is just 1. Now we know that the derivative of this function right here will be 2x. So from the chain rule, we know that d over dx of g of h of x is equals to d over dh g h of x times d over dx h of x. So first we compute the derivative of g on the output of the inner function, and then we multiply that with the derivative of the inner function. But you might be asking, how do we find the derivative of this sum term right here? So using the sum rule, we can deduce that the derivative will be equal to the derivative of each term added together. It will be the derivative of the first term plus the derivative of the second term till the derivative of the last term, right? So now we know that the derivative with respect to w of f of wb is x to the I, and with respect to b it's 1, and that the derivative of g of x is 2x, and our function is right here. This is our function. We need its derivative. So how do we compute that? Using the chain rule, we can deduce that it will be the derivative of the outer function computed on the result of the inner function times the derivative of the inner function. Let's first solve this term right here, which will be 2 f of wb, since the derivative of g of x is 2x. So its derivative will be 2 times this 2 f of wb, and the derivative of this term right here, we know that it's xi. If we expand this function right here, it would turn to this, and that is the derivative with respect to w. Now for the whole cost function, we will sum up all these derivatives and divide by 1 over 2m, which will not change the derivative since it's a constant multiplier. Remember I told you earlier that we divided by 2 so that the calculations become neater. It's right here. So there's a annoying 2 right here which can be cancelled out by this 2m. So we are left with 1 over m, then 1 over m times the sum of wxi plus b minus yi times xi. And the process will remain more or less the same to find the derivative with respect to b, except that this term right here, if you remember, its value was the derivative with respect to w. So it would become the derivative with respect to b, which would be 1. So this is a 1 right here, but we don't write it since we're multiplying by 1. Similarly, we can cancel the 2's out right here, and we have got the derivative of the cost function with respect to b and the derivative of the cost function with respect to w. Thanks for watching, and next video we'll continue by implementing linear regression from scratch in Python in a code along.